Hello, in this video I'm going to talk a little bit about trigonometric identities. Now, whenever we think of an identity, one of the simplest ones is like, say for example, you have x plus 3 to the second power is equal to x squared plus 6x plus 9. Now, one way of which that you would know that this is an identity, for example, is that you would have to have that the left-hand side would have to equal the right-hand side. So, for example, if I was to expand x plus 3 to the second power as so, I know that if I multiply x plus 3 times x plus 3, that if I implement any procedure of foiling or distribution method, that in either case you end up with like x plus 3 multiplied by x plus we have x plus 3 multiplied by 3. So this would give us x squared plus 3x plus 3x plus 9, but that's the same thing as x squared plus 6x plus 9. So in this sense, we know that this in fact is definitely a true statement. Now the other types of identities though that you'd be looking at would be, say for example you have that cosine of theta. You know that the cosine function can be rewritten as 1 over secant of theta. Or, by definition, you would then say, for example, that if you were to multiply cosine of theta times secant of theta, this would in fact equal to 1. And that's basically kind of true, because you have that those are the relationships between those two reciprocal functions. Now, similarly, you would have that sine of theta, its relationship to its reciprocal function would be 1 over cosecant of theta. Now, of course, this would be the same thing if you were to multiply the two, that it would in fact give you 1. Now, of course, one way that we could say, for example, if I wanted to prove these statements, then one way that you could do that is you could say, well, you know that sine theta is y over r. But then you also know that cosecant theta, by definition, is r over y. Now, if that's the case, then basically, if, for example, you were to take 1 over cosecant of theta, this would equal to 1 over r divided by y. But that's the same thing as y over r, which is equal to sine theta, which in fact, in this case, is true. Okay, now we don't necessarily have to conclude every single statement with true or not. We can always say thus has been proven, or QED, or just put like a little square box. Now the other thing that we can look at is, for example, like tangent of theta. Well, tangent of theta and its reciprocal function by definition is cotangent of theta. Now, in this case, there actually are multiple ways that we can prove, for example, like tangent theta equals 1 over cotangent theta. But, you kind of get the idea that if you were to substitute, then in that case, it would give you what you want. Now, these are just the reciprocal functions, for example, but you also have your quotient identities. So, for example, I can say that I know that tangent of theta is equal to sine of theta divided by cosine of theta. That's one of the quotient identities that you've been using throughout this chapter so far. The other would be that you could look at cotangent theta equals to cosine theta divided by sine theta. Now, of course, again, you can try to prove these, but right now I'm not really trying to prove like every single identity, for example. This is just to give you an idea of like which identities that you'd be using, um, respectively. Like if, for example, that you needed to prove something, or if you needed to rewrite something, or if you needed to simplify something. So, okay, so yeah, these were the reciprocal identities. Now, you also have that, for example, that we can look at some of the Pythagorean identities. Now, usually we use the term fundamental identity, but it's really the same thing. So recall like how we have x squared plus y squared equals to 1. Now, basically, for example, if I was to say that x is equal to cosine of theta and y is equal to sine of theta, if I substitute into this equation, basically I get cosine squared theta plus sine squared theta is equal to 1. This is actually one of the most fundamental identities that you'll ever work with in regards to the Pythagorean identities. Cosine squared plus sine squared is equal to 1. Now, others will say sine squared plus cosine squared equals 1, but it's really the same thing. Now, the other identity that you would use, for example, is let's say that we're already sure of this identity right here. If I was to divide this identity on both sides by cosine squared, I would get, first of all, I would have cosine squared theta divided by cosine squared theta plus sine squared theta divided by cosine squared theta equals to 1 over cosine squared theta. But we have that from our identities that basically this gives us 1 plus tangent squared theta equals to secant squared theta. Now, keep in mind that uh, you already have the first identity up over here, so this is the second one. Okay, so if I wanted to solve for tangent, I can do that, or if I want to solve for secant, I can also do that. Now, the other type of function that we do have is, or the identity, is, for example, if I take this original fundamental identity and divide by sine squared instead, well, you have that similarly, you're going to end up with 1 plus cotangent squared theta equals 2. Okay, so we're dividing by sine squared on both sides. So that's going to give us cosecant squared theta. So this is our other fundamental identity. Now, of course, if I wanted to solve for cotangent, I can solve for cotangent, for instance. Or if I wanted to solve for cosecant, I can solve for cosecant. Okay. Now, how you would use this in an example, for instance, you could probably say that if we have the expression tangent of theta multiplied by, let's say, uh, let's see, well, let's go ahead and just put like, for example, cotangent theta plus 1. Well, we can actually solve this because essentially this is like saying if you have tangent theta and then you know that this is 1 over tangent of theta because they're reciprocals of each other, you can actually just distribute. When you distribute, this will give you 1 plus tangent of theta. Now, in this regard, there's not much to do because of the fact that it's already simplified as it is. So yeah, there's not really a whole lot to do whenever you have something like this. Now, other identities that you actually might use in this chapter, and especially in 5.2 and so on, is uh, this characteristic. So I'll just call this like a special identity. So for instance, if I have cosine of negative theta, this is the same thing as cosine of theta. But if I have sine of negative theta, this is the same thing as negative sine of theta. Okay. Now, mostly you'll be probably required to simplify expressions in addition to, using these identities. So let's go ahead and look at another example, for instance. So let's say that you have, okay, so let's say that you have cosine of theta divided by 1 minus sine theta. Now, whenever you're given an expression like this, there is a way to rewrite it. Now, to rewrite it, basically you have to multiply by the conjugate. Okay, so typically some questions might ask you to rewrite or to simplify. Now, what we'll do is we'll just say, okay, well, we have cosine of theta, and that's all divided by 1 minus sine theta. And this is equal to, well, actually, let's not use equal. Okay. Now, what we're going to do here is we're just going to multiply by 1 plus sine theta divided by 1 plus sine theta. Now, if we multiply across, okay, so this is still equals. If we multiply across, we kind of don't want to do that. So let's just go ahead and just leave it like 1 plus sine theta. And this is all going to be divided by 1 minus sine squared theta. Now, the only thing about this is that basically you have that there is an identity that will replace for 1 minus sine squared theta. Now, that's actually cosine squared theta. So that means that you're going to have cosine of theta multiplied by 1 plus sine theta, all divided by cosine squared. Now, interestingly enough, properties of exponents says that basically that one of these will cancel out. So now I'm close to finishing the problem. So now I have that this is going to be, okay, so we have 1 plus sine theta all divided by cosine theta. Now, basically, if I were to separate this, this would be 1 over cosine theta plus sine theta over cosine theta. Now, notice that, for instance, that basically what ends up happening here is that you're left with secant of theta plus tangent of theta. And then that's it. Okay. So in this case, like all that we did here is we just multiplied by the conjugate on top and bottom, and then we just rewrote it. So most of the time you'll probably just be asked to just rewrite the expression. Now let's try another question where we try to simplify and rewrite. So let's say that we want to simplify the following. We have 1 minus sine of x plus 1 over 1 plus sine of x. Now, we know that basically we can combine like terms using common denominator. So the common denominator between these two is basically um, 1 plus sine x and then 1 minus sine x. So we're going to multiply this by 1 plus sine x over 1 plus sine of x multiplied by our expression, sine of x, and then we have that we're going to multiply this by 1 minus sine x over, over 1 plus sine of x. Okay, now we have that we'll multiply it then by 1 minus sine of x as well. Okay, so that'll be equal to 1 plus sine of x. Now, these two are going to have the same denominator, so basically we can actually just combine like terms. And all of this is divided by 1 minus sine squared of x. Now, essentially, we have that we're almost there because we have that all that we need to do from here is to cancel out the sine of x on both sides. So what ends up happening is that you end up getting 2 divided by 1 minus sine squared x. Now, earlier we kind of said that sine squared x is going to be cosine. So this is going to be 2 divided by cosine squared x. However, we know that basically this will be 2 secant squared x. So essentially that whole expression simplifies nicely to 2 secant squared x. Okay, now let's go ahead and think about how we can look at fundamental or just some identities like verification. Now, usually whenever you have like an identity, so essentially the idea is that you want to be able to show um, that the left-hand side is the right-hand side. So for example, if I have tangent theta plus secant of theta to the second power, and this is equal to 1 plus sine theta divided by 1 minus sine theta, there's actually many different ways that we can show this. Either, we can show that the left-hand side is going to be the right-hand side. Okay, so that's one way that we can do that. Or vice versa, we can show that the right-hand side is the left-hand side. Now there is also a form of type of transitivity, like if we have that let's do it like this. Like if we were to think of like if A is equal to C and C is equal to B, then that must mean that A is equal to B. Well, we can do it like that too, but sometimes that might actually be a little bit more tricky. Okay, now the rule of thumb with basically kind of like solving or verifying an identity is that you work the most complicated side. Now in this case, note that the most complicated side would probably be the one with the parentheses, um, but in actuality it kind of doesn't matter technically as long as we have some consistency. So let's do it like this. We'll go ahead and show that the left-hand side is the right-hand side. So I'm going to take the tangent of theta, secant of theta to the second power, and I'm going to rewrite using the quotients. So I have sine theta divided by cosine theta plus 1 over cosine theta. All of that is to the second power. Now, From here, I'm actually going to go ahead and rewrite it like the sine theta divided by cosine theta, and there should be like a plus 1 there. Okay, now all of that is raised to the second power. Now notice that this is going to give you sine theta plus 1 to the second power, but all of that is divided by cosine squared theta. Now, interestingly enough, I have that the cosine squared theta is actually, it can actually be rewritten in the following manner. Now, let's go ahead and say that we have sine theta plus 1, and that's squared. Now, cosine squared is actually 1 minus sine squared theta. However, I know that this can actually be factored. So what ends up happening is you have sine theta plus 1 to the second power, and all of this is divided by 1 minus sine theta multiplied by 1 plus sine theta. Well, it looks like one of these two actually cancels out. So we have that cancels out and that cancels out. So what gets left behind on the right hand side is that you end up with basically 1 plus sine theta all divided by 1 minus sine theta, which actually is basically everything that you needed, okay? Or it's all that you needed, because you just needed to show that that was equal to that right-hand side. Now, in class, normally I'd probably say that if we were going to work backwards, we would just need to multiply by the conjugate, or yeah, just work your way backwards. Because now that you can see that the left-hand side is the right-hand side, then it kind of works itself out. Um, Now, I guess you could probably foil it, but that probably may be a bit much in either case. So this is probably like the fastest way to do it, to be honest. Now let's try just one more identity problem. So we want to do the same thing. We want to establish or verify the identity. So let's say that we have 2 cosecant of x equals to secant of x minus 1 divided by tangent of x, and this is going to be should be plus tangent of x divided by secant of x minus 1. Okay, now there's probably several ways that we can do this problem, but the main thing though is that we realize that essentially the rule of thumb says that we work the hardest side. So in this case, that would be the right-hand side. The way that I would phrase it is, we work the most complicated side, which in this case happens to be the right-hand side. Okay, so in this case, we're showing the other way around. We're showing that the right-hand side is the left-hand side. Now, mathematically, yeah, we could show that left is right, right is left, and then that's that, right? But here it's just that we're only going to show one part of it. We don't need to show like both sides of it. So I have this expression secant of x minus 1 divided by tangent of x, and it's being added to tangent of x, let's see, and all of this is divided by secant of x minus 1. Okay. Now, there's many different options that we could go about this. Let's see. One would probably be to try to combine like terms using common denominator. That may work out, but let's see. So, how about this? Why don't we explore the option of just, transcribing this into basic terms. So cosine, minus 1, and then that's all divided by sine of x divided by cosine of x. This is going to be the same thing, so sine of x divided by cosine of x, and all of this is divided by 1 over cosine of x minus 1. Now, it looks that I can go ahead and just multiply by cosine on top and bottom. So in that case, what's going to end up happening is that if we multiply by cosine on top and bottom, so like cosine of x and then cosine of x, and then over here, same thing, cosine of x, cosine of x. Basically, this is going to give me 1 minus cosine of x divided by sine of x. Now, furthermore, this is also going to give me plus sine of x, and then I have 1 minus cosine of x, and this is all divided, right? Okay. Now, earlier I mentioned that basically that we can combine like terms by using, again, the common denominator. But I noticed that if I was to multiply this by 1 over cosine, or I'm sorry, 1 plus cosine of x divided by 1 plus cosine of x, that we can actually, basically introduce cosine squared, but then rewrite it as sine squared and then just simplify. But don't worry, I'm going to write out 1 plus cosine of x divided by 1 plus cosine of x. So what that's going to give me, and we're running out of room, we have 1 minus cosine of x divided by sine of x plus sine of x divided by 1 minus cosine of x. Now actually that's going to be cosine squared x, right? And we should probably put 1 plus cosine of x. Okay, now what ends up happening is that we have that this right here, that right there is sine squared x. So that means that we have 1 minus cosine of x, and all of this is divided by sine of x, plus sine of x multiplied by 1 plus cosine of x. Okay, so we didn't multiply. We didn't distribute, right? This is divided by sine squared of x, but properties of exponents tells me that that cancels out. So we end up with the following. We end up with 1 minus cosine of x plus 1 cosine of x, and all of this is divided by sine of x, because now they have the same denominator. So what ends up happening now is that you end up with that those two right there, they cancel each other out. But 1 plus 1 is 2. So we have 2 divided by sine of x, and all of that is going to be 2 times cosecant of x. Now, that's the final result, right? So here we just need to look back and see, is that exactly what it was? Yeah. Okay, so that means that basically we showed that, we proved that the right-hand side is in fact the left-hand side. Now, sometimes you do have that some identities may not actually be what they say they are. So in that case, whenever you get like a contradiction, then you would just say that, it's not an identity in that sense. Now, there is another way to actually prove statements, for example, like such as I can say that if I have an equation like, say, for example, sine of 2x, I can probably show that, this equation and another equation like 2 cosine of x, sine of x, that these both are the same. But I would do that by graphing it. Now, another one that we can look at, for example, is let's say that you already had a statement like cosine of x is equal to negative sine of x minus pi over 2. Okay, we don't want that. X minus pi over 2. And then we just go ahead and figure out, are these two in fact the same? And the answer is yes, because, for example, if I graph y equals cosine of x, well, there it is right there. Okay, so we have that, yeah, if we graph that, we get this equation right here. But if I graph the other one, y equals negative sine of x minus pi over 2, well, it just so happens that they overlap each other. So what that essentially means that if they're coincidental, then they are the same graph. So then in that case, I would have to say that these in fact are uh, equal to each other. Well, similarly, you know, we can actually say the same thing about like the following equation. Y, so let's get rid of this. Y equals, so like sine of 2x. Okay, so I have that this has a period of pi. But if I rewrite it as 1, well, not 1, but as 2 sine of x and then cosine of x, it's in fact the exact same equation. So in this case, okay, it's getting picky. Okay, so these two equations are the same based on just their graph. So, for example, if we were to mess around with the tangent function, like if we have y equals tangent of x, and then, for example, I said that we wanted to look at cotangent of pi divided by 2 minus x, well, you would see now these are the same functions too. Okay. Now, when we move into the formulas for adding, like a plus b or a minus b, you'll basically see that when you expand them, that is another way that you can prove those equations. But for now, we're just going about these algebraic methods that we used in both the sections 5.1 and 5.2. Okay, so be sure that you do kind of review the formulas that you are given, so that way that you can essentially take any statement and verify whether it's true or not, or that you're just establishing it.